you, okay, and you get points for that. Okay. Yep. Any questions about that, please? Hmm? Is everything clear about this? The papers are found on Moodle in a folder called Papers to Study for Exam, something like that. I know I gave it a name to suggest that these are the papers you need to do as a take-home exam for the final grading. Okay. So I talked about assignments. Now, returning to the subject of this lecture, last time we discussed and we sorted out the topic of Lyapunov stability. I need to remind you that Lyapunov stability for a nonlinear system is with respect to the deviation of a trajectory from a reference trajectory. In general, as you've noticed, the reference trajectory is the origin, okay, which is considered to be an equilibrium of the nonlinear system. And this is without loss of generality, because any system at any equilibrium point can be shifted, can be changed, can be amended so as to have an equilibrium in the origin. We can always do that. Hence, the discussion about the origin is general and proves the point of this idea. Furthermore, Lyapunov stability is related to energy. So the idea is that if you perturb the reference solution and the internal energy is decreasing, of course, the desired thing is to have a monotonous decrease. This is not always possible. Actually, this is always not possible, except in a few specific situations. So, if the energy is decreasing to a constant level or to zero, and the trajectory is going towards the equilibrium, to this zero energy trajectory, which is the equilibrium, then the equilibrium point is asymptotically stable. Of course, to prove asymptotic stability is many times is very difficult and cumbersome. Why? Because these are only sufficient conditions. They're not at all necessary, meaning that the Lyapunov functions we create are not unique. There's an infinity of Lyapunov functions out there for a system, for a given system with a specific equilibrium point in the origin. Yeah, and we showed things like that previously. If you look at any linear system and you consider the creation of the solution of the Lyapunov equation, okay, then that solution yields a monotonous, and the solution is positive definite, then you can get a monotonous decrease of the energy function, okay? So V dot, I remind you, V is the Lyapunov energy function, Vxt, which is positive, 0 in 0, okay? Positive definite, 0 in 0, okay? And if V dot is constantly decreasing, and this happens in the case of linear systems, then things are all right, and the origin is asymptotically stable. And this is easily corroborated with the eigenvalue theory for linear systems. Of course, the results for linear systems are global results, which is not the case for nonlinear systems, where these results are most of the time local. They can be globalized if you're able to find the domain of attraction. And if the domain of attraction, where the energy comes from a specific bound and goes to another specific bound, constant bound, if you can prove that this domain of attraction is the whole state space, then you hit the jackpot and your stability property is global. But this is seldom the case. Most of the times this is not true. Or even if it's true, and even if the engineering and the mathematical and our intuition, the gut tells us that this happens, this is true, many times or many a time, this task is next to impossible to achieve. So it's almost impossible to prove with the mathematical, even with the advanced mathematical tools that we have. Okay. Of course, people nowadays are using machine learning. I'm sure you've heard of that. They're using machine learning to prove Lyapunov stability, because machine learning can provide numerical tools to be able to create such things. Okay. For instance, if you have, let's go back to the linear case and discuss a little bit. So if you have a second degree equation, okay, if you have a second order, differential equation, linear differential equation with constant real coefficients, okay, such as y dot plus, say, 3y dot plus 2y equals 0. Yeah, this is a mechanical oscillator, this is an RLC circuit, and so on and so forth. It can be anything. This is easy to find, that you can get this to be x1 dot is x2, x2 dot is minus 2x1 minus 3x2. Okay, this means that x dot is fx with fx being x2 and then minus 2x1 minus 3x2. Okay. You have the following. I'm not sure if we discussed this before. We have the following situation. How do we prove that the origin is an asymptotically stable point? Okay, so prove that the origin is asymptotically stable. Have we done this last time? Did we do this last time? Do you remember? Did we discuss this last time? Well, never mind. We do it again. So how do you do this? You have two options. The first option, which is very handy, you look at this, you consider this a mechanical system, and then you take a Vx, the energy function, to be the total energy of this guy. Okay? And this is the kinetic energy plus the potential energy. Okay? This is positive. Definite Vx is 0. V0 is 0. V0 is 0. Okay? And you also get the gradient of this guy, so you get dv dx to be x1, x2. So this is x transposed. Okay? So essentially, this guy is half x transposed x. Or if you want to put it in a matrix format, this is half x transposed identity x with the identity positive definite matrix. The identity is a positive definite matrix. Okay. And then you do v dot x, and this is dv dx, I remind you, fx. And this is x1, x2. Maybe I need another constant here. I'll check it out in a minute. I think I actually need here, I need something else here. We are going to change this constant, possibly. There is this possibility. So this is x2. This is minus 2x1 minus 3x2. So this is x1, x2. And then you get minus 2 x1, x2. So you actually I need here, where do I need it? Because I need it to be here 2x1, right? 2x1. So here I need to multiply with the elastic constant. Yeah, 2 is the elastic constant. So this is 2 times half x1 squared. And then this is 2. And then this is 2. Okay. And then you get this minus 3x2 squared. These two cancel each other. Okay. And this is less than or equal to 0 for all x1, x2. For all x1, x2. So that means that in this case, the origin is only stable. But you need asymptotic stability. Then you have to go to LaSalle principle. Okay. So x2 dot equals 0. Okay. If x2 dot equals 0, okay, and x2 is 0, so we need to see the case for x2 equal to 0. Okay. x2 equal to 0. x2 dot equals 0 as well. So where is this energy constant? Only at the trivial solution, because this goes only to x1 equal to 0, unique solution. Okay, so the invariant set. You get the invariant set. And then, indeed, using LaSalle, the origin is asymptotically stable. But this is not unique, because the second choice you can make is Vx is half x transpose px, with p that you'd like positive definite. True? It's true. And you need to solve the Lyapunov equation A transpose B. A transpose P plus PA equals, and here you need minus Q. So essentially you can take minus identity. You can take minus the identity. Okay. So you select P to be P11, P12, P12 because P22, P needs to be symmetric. And we substitute. So you do 0, 1, minus 2, minus 3 times P11, P12, P12, P22 plus P11, P12, P12, P22 times 0, 1, minus 2, minus 3. This equals minus 1, 0, 0. And here we get a system of 3 equations, actually. 3 equations in the unknown P11, P12, P22. Let's check it out. So you get P12 plus minus, sorry. So P12 minus 2P12 equal minus 1. So this means P12 equal 1. Right? The second equation. P22 plus P11 minus 3P12 equals 0. Okay? So this means that P22 plus P11 equals 3. And the last equation, we do not consider this corner because this is symmetric. And if you check, it's the same equation. The last equation is minus 2P12 minus 3 P22 plus P12 minus 3 P22 equals minus 1. Agree? I hope it's not wrong. So this is equivalent to minus P12, but P12 is 1, so it's minus 1, minus 1, minus 6 P22 equals what? 0. Zero, huh? So that means that P22 is what? 1 minus 1 over 6. This is P22. And then you get here P11 is 3 plus 1 over 6. So P11 is 19 over 6. P11 is 19 over 6. And P12 is 1. So that means P is what? 19 over 6. Unique solution, okay? It's a unique solution. We know that from Lyapunov equation theory. 19 over 6 minus 1 over 0. No, sorry, P12 is 1. So 1 minus 1 over 6. Okay? Is this positive definite? Let's check it out. P lambda, the characteristic polynomial, okay? Characteristic polynomial. Lambda squared minus minus 18 over 6, so minus 3 lambda, okay, minus 3 lambda plus determinant, minus 19 over 36 minus 1, so it's minus 19 minus 36 over 36, so this is what? Minus 55 over 36 minus 55 over 36. This is the characteristic polynomial. Okay. Correct? So now you got a question? So now we continue the computation of the solutions. That means that the discriminant, this is a second degree equation, okay, equals 0. Second degree algebraic equation is 9 plus 4 times 55 over 36. Okay. All right. I hope I'm right. So this is 9. So this is 81 plus 55 over 9. And this is 146. No, 136. 136 over 9. And lambda 1, 2 is 3 plus minus square root, or not, no, I don't need the square root here. I don't need the square root. So this is plus minus square root 136 over 3 over 2. So this is 9 plus minus square root 136 over 2. Are these positive? Huh? Are these positive? I made a mistake. No one told me. I didn't do a transpose here. That's why it's not correct. Oh, come on. No one told me that. Why didn't you pay attention? A transpose is the first equation, so it's all wrong. We have to start from scratch. We have to start from scratch. It's A transposed here. So it should be like this. Transposed. That's the mistake. That's why the solution is not correct. You didn't tell me. It's wrong. I'm trying to delete everything and start the computations from scratch. Start the computations from scratch. Sorry about that. Because you see, how did I know that? Because these were not both positive, and the solution needs to be positive definite, because A is stable. I know that from linear system theory. A is stable. The eigenvalues of A, or the characteristic polynomial of A, is a Hurwitz polynomial, right? Okay, so let's start again. So if we transpose this matrix, this is 0, 1. So here I get -2. Here I get 1. So let's start again. No, the transpose need not be here. Shouldn't be here, the transpose. Okay, so now this is correct. So -2 P12 -2 P12 is -1. I'm just multiplying the matrices. So this leads to P12 is 1 over 4. Second equation, this corner, -2 P22 plus P11 minus 3 P12 is 0. So this leads to the equation -2 P22 plus P11 equals 3 over 4. And the last equation is P12, so that's 1 over 4. P12, that's 1 over 4. Okay, I'm just multiplying the matrices. -3 P22 plus 1 over 4 minus 3 P22 equal -1. Agree? Is it correct? P22, P12, P22. Okay, fine. So -6 P22 equals -1 -1. So this is -2. No, -3/2, sorry. Okay. 6 goes away with the 3. Here's 2. So P22 is -1/4, right? It's 1/4. Hence, P is, oh, and P11, we should get P11 from here. So P11, yes.
P22 has a minus in front of it. It should
Oh, sorry. So it's
positive.
plus.
Yeah,
This is plus. Right. Correct. So P11 is 3/4 plus twice 1/4. So it's 5/4. Okay. So this is 5/4. 1/4. 1/4. 1/4. Something like this. This is P. Agreed?
Yes.
And I think I don't need to check the eigenvalues. I think I'm going to check it. I'm going to check the definition. Okay. Let V, V1, V2 non-zero. So V transpose P, V, V1, V2, 1/4. Then it's 5, 1, 1, 1. V1, V2. Okay. So this is 1/4. Now I do the multiplications. 5 V1 plus V2, V1 plus V2, V1, V2. This is 1/4, 5 times 5 V1 squared plus V1, V2 plus V1, V2 plus V2 squared, right? I think it's correct. Yeah. So this is 1/4 times 5 V1 squared plus 2 V1 V2 plus V2 squared. And actually this is 1/4. It's easy to check. 4 V1 squared plus V1 squared plus 2 V1 V2 plus V2 squared. This is 4. And this is V1 plus V2 squared. So this is positive for all V1, V2 real numbers, okay? Okay, so this is a positive definite matrix. This is positive definite. Wonderful. Wonderful. So now Vx is half x transpose times 1/4 here. So it's 1/8 actually. X transpose 5, 1, 1, 1, x. Right? Which means that dv dx is x1, x2 times 5, 1, 1, 1. It's easy to prove. So if you have Vx is x transpose Px, okay? So this is half, yeah? So this is half x transpose P plus half, when you take the derivative, sorry, the gradient, I mean the gradient, yeah? Then dv dx is half x transpose P plus 2 px, but P is symmetric and positive definite. So this is twice the same thing. This is x transpose P. Okay? So this is what? 5x1 plus x2, okay? And x1 plus x2. This is the gradient. And now, v dot x is 5x1 plus x2. I hope I'm right. Okay. I really do hope I'm right. Plus, and then this is x1 plus x2 times f. So that's x2 minus 2x1 minus 3x2. This is f, right? This is fx, if you remember. Okay? So now we just do we just multiply. So this is 5x1 x1 x2 plus x2 squared minus 2x1 x2 minus 3 x2 squared. Okay? All right? So this is 3x1 x2 minus 2 x2 squared. Okay? I think there is something wrong here, because this should be negative definite by all means. This should be negative definite for all x. What's wrong? So here you have dv dx is I think I forgot something. There should be a 1/8 somewhere. Agree? There's a mistake. There's a little bit of a mistake here. Let's see where it is. So dv dx. Okay. Okay, this is multiplied here by 1/8. I don't think that changes too much things. So essentially Vx is 1/8 5x1 squared plus we take it from here, take this relation, plus 2, this one, plus 2x1 x2 plus x2 squared, right? And now the gradient, maybe I'm wrong, but I don't think I am. And dv dx is 1/8 10, okay, 10 x1 10x1 plus 2x2, okay? And then you get 2x1 plus 2x2, agree? But then 2 you can cut, and this is 1 over 4. 5x1 plus x2, x1 plus x, so it's correct. It was correct. Then multiplied by f, multiplied by f, but I didn't do the computations right here. You didn't tell me again. Oh, Jesus. The computations are not right because the multiplications are wrong. Okay. So let's do the computations in this part once again. Start again. This is wrong. So again, 5 x1 x2 plus x2 square, and now you have minus 2 x1 square, I forgot about this, minus 3 x1 x2 minus 3, once again, minus 3 x1 x2 from this guy, no, sorry, x1 x2 from this guy. True? Minus 3 x2 squared. Now this is correct. Now this is correct. Okay, multiplied by 1 over 4. 1 over 4. But that one, that positive constant is not changing anything. Okay. So now you have minus x1 x2 . So we did away with these terms. Minus 2x2 square minus 2x1 square. Correct? True? It's true, isn't it?
Can you maybe scroll a little bit out that I can see the left side of the two matrices to like not
This?
zoom in, like zoom out that I have, because currently we can't see what's like on the left side. That's why like it's a little bit hard.
Where? Oh, here.
Yeah.
Yeah. So no, I'm just multiplying these two matrices. This vector, this line with this column. Yeah. It's a line multiplied with a column. True?
Yes.
Okay, so I'm just adding up the terms, and now I'm canceling out. I have to zoom this in. So this, and this give this. Then you have this and this. Okay, that's all that's left. Agree?
Yeah.
Agree. Right. Okay. And this indeed can be shown that is negative definite for all x1, x2. So this means indeed that 0 is asymptotically stable. But you see, this is much more difficult, that's what I wanted to show you, than employing the principle of LaSalle we had earlier. It's much more difficult, okay? It's much more difficult. So the first option, the easy energy function, was very nice, wasn't it? This one is much more difficult. Of course, it's not difficult because it's linear and you can use MATLAB. You can use MATLAB, okay? But if you remember, the third option was using the observability. Using the observability, okay? How do you do that? You pick an output. You choose an output. Choose the output y equal, for instance, the position 1, 0 times x1, x2. Okay? And to check the observability, what you do, you can from linear system theory, you construct the observability matrix. Observability matrix, which is CA. So this is 1, 0, 1, 0, and CA. Usually this takes out the first line out of the matrix A. 0, 1. That's the first line of the matrix A. Where's matrix A? Where is matrix A? Matrix A. I can't see the matrix A. Oh, this is a linear system, yeah. So this is easily written as AX. This is easily written as AX with A equal 0, 1, minus 2, minus 3. Just do the multiplication with X. So the first line is 0, 1. So indeed, this is the identity. And this has rank 2. This is invertible. So we know from linear system theory, which you can recap, we know that this is invertible. This has rank 2. So that means that the system x dot is fx, y is cx, okay, this is ax, is observable. We know that from linear system theory, is observable. And then if it's observable, then there exists the observability gramian. So you can solve the equation A transpose M plus MA plus C transpose C equals 0. This is the observability gramian. So M is the observability gramian. This is the observability gramian. Yeah, you know that from linear systems theory. Okay. Well, I do remember, Florian, I think you asked me for some slides and the book of linear systems theory. Did I give it to you, or did I forget about it?
No, I think you uploaded it already to the files section, but I will have a look.
But did you get the material from me?
Yes, I think so.
Oh, cool, fine. So you can check it out in the material. What the things I'm talking about right now, you can check them yourself in the linear system theory stuff you've got from me. So you have this equation, okay? So you can repeat the procedure and solve the gramian, and then of course you'll get the same result. Okay, so these are 3 ways to apply this theory to linear systems. But what I actually wanted to emphasize is something that I mentioned last time, is that you need to pick the simple Lyapunov function if that's possible. So you usually start from energy, if you can understand from a physical point of view your system. Otherwise, to construct a Lyapunov function is kind of difficult. In the book of Khalil and in other reference books, there are methods quite tedious and quite complicated, helping you or showing you how to build a Lyapunov function from scratch, more or less from scratch. Furthermore, as I've just mentioned, there's machine learning, and these neural networks and artificial intelligence, which can help us can help us build Lyapunov functions. I actually have, I think, if you check on Moodle, I'm not sure if I have already uploaded for you. There are some references of with Lyapunov functions based on machine learning. I'm going to show them after a break. Let's have a break now. And after the break, I'll try to find some references with this respect. I hope I can find them, okay? Because I have something. So let's have a break and we meet again soon, okay? Thanks.
Okay.
Okay, I'm back. Hold on a second, please. This. This. Pick this. Today, this is Wednesday, right? Wednesday. Okay. Fine. I'll try to attach to this notebook. Let's see if we can do this. Try to attach something. To attach on one of those files. Telling us about Lyapunov function in machine learning. Okay. So, materials. Machine learning. Lyapunov function machine learning. So I've got some references. I'm just checking which one is better. Which one is better? Yes. For instance, okay, I'll share a different screen. I think this is easier. And then I'm going to put all these papers for you to study if you're interested in the subject. Okay. So, I'll try to share the other screen. Let's see if I do this guy. This is not right. Sorry. Let me try again. So share screen, window, this one. Okay, can you see the screen with the file?
Yes, it is visible.
It's visible, right? So we've got this paper, you see? It says here Lyapunov control, learning control Lyapunov function to ensure stability of dynamical system-based robot reaching motions. So you have a mechanical system, okay? And here they show you the movement, okay? You see here, this is the phase plane, you see? Xi2 versus Xi1, okay? A tennis swing composed of a swing and a resting phase, okay? And this is the, you see here, this is the dynamical system, look here. D is the dimension of the system, okay? And this is the stabilizing command you see here on the second column. I'm talking about this part. So the stabilizing command must provide corrections such that you have a negative direction for V. So you want to imply Lyapunov theory. And how you do that, apparently, you can build a learning control Lyapunov function. You see? Look here. And this guy, so this block here, yeah, this block here, provides a command U, a stabilizing control U based on Lyapunov theory. And here is the approach used to build the Lyapunov function. Okay, all right. The learning approach. This is I'm not familiar with, but you can look, and here is the stabilizing command, equation number 10 on the second column. Okay, so these are quite interesting things, and this is the algorithm. This is the algorithm. Okay, maybe I can upload these guys as well for you on Teams, so you can further study. Okay, let me see. Let me find another one because I've got more. I collected them. Let's open all of them and see if there's anything interesting in all these things. So you can do research and look at these things. So using machine learning to replicate chaotic attractors and calculate Lyapunov exponents from data. Okay, so this is a bit more difficult. Okay. You can see all sorts of relations, okay, for optimization. Okay. You see? Look, this is an interesting system you can study with everything we've done so far. This guy at number 5, you can check it out. And then they present here some learning algorithms to be able to create the Lyapunov function. So Lyapunov theory is starting again to be very popular, actually. This is my point now. This is my point. Everyone wants to do Lyapunov theory. You see constructions of neural network-based Lyapunov functions. Look at this one. This is also a very interesting paper. Okay? Because you people, I know you're interested in all this modern stuff. So here it is, the modern stuff presented to you. Okay? And so on and so forth. Okay? So would you consider these to be interesting papers? Do you want me to put them on Teams for you? I can upload them for you. Would you study them? Would you look at these things?
Yes.
Okay. I suppose you would. Okay, cool. I'm going to do that for you. So Lyapunov theory, very popular, very nice. Lyapunov theory, of course, is very useful to be able to do control. Okay, we'd like to do control with this. We'd like to do control with this. And how are we going to do control with this? There's multiple ways of doing it. Actually, if you look very closely, even the Kalman filter theory can be considered a particular case of Lyapunov theory. Okay, a particular case of Lyapunov theory. Also, in the book of sorry, in the book of Khalil, you'll be able to find other interesting control techniques based on this theory. We are going to touch two subjects with this respect. For instance, for you to study, I'd like you to study passivity-based control. Passivity-based control. Passivity-based control maybe is the most energy-related because it's energy-based control. And energy-based equals or indicates or is bijective or is one-to-one with the Lyapunov theory, because the Lyapunov theory is about energy functions. But we are going to touch two very interesting cases. One is called absolute stability, and this is going to yield us some linear criterion for a nonlinear problem. This is very interesting for a special class of nonlinear systems with static nonlinearities, which is very popular. Used to be very popular at a certain point, then it disappeared. People thought this is not so popular any longer and this is not so interesting anymore because the models are not like that. But actually, a few years ago, 2 or 3 years ago, at the European Control Conference, if I remember correctly, it was held in Cyprus back then. I remember having seen quite a number of presentations related to this subject and indicating the possibility of doing control based on this Popov criterion line of thinking, which we are going to present right now. The second subject, which is going to be starting probably next week, and for the last few lectures, I'm not sure if we're going to have all of them or just some of them, we are going to talk about feedback linearization, another specific nonlinear control technique, very specific, with a scope of doing control in some linear manifold, if you like, so projecting essentially the nonlinear system onto some linear manifold, and being able to do that, we can achieve some control goals such as closed loop stability. Okay. But first things first, and let's talk about absolute stability as a first application of the Lyapunov theory. Okay. This is a direct application, and as we'll see as the algorithm is developing, this is quite interesting. So the historical importance of the absolute stability problem, first of all, apparently it's been formulated during the Second World War in the Soviet Union. Okay, so as always, problems given by the Russians. Okay, and the solution to that specific problem was this Lyapunov approach. And later on, the problem being developed on and on, the Romanian Popov in 1959, famous nonlinear and linear control guy, apparently is sort of like the most famous of all of them. He died in 2000, and there was a special issue of the European Journal of Control about that. So the name of Popov, you remember from the Popov, Hautus-Belevich Popov controllability and observability criteria for linear dynamical systems. And then you heard about the Kalman-Yakubovich Popov lemma for optimal control, the famous Kalman-Yakubovich Popov lemma, which is a crucial result in dynamical systems theory. Due to that result, loads of things could happen afterwards. Essentially, that's also based on some Lyapunov way of thinking. Okay, the Kalman-Yakubovich Popov lemma, it's actually a consequence of the Lyapunov theory. Kalman Yakubovich Popov lemma, indeed. Turning point in the development of modern control theory. It's very nicely expressed in this phrase. And then there is the Popov criterion for absolute stability. And here we have the line, the Popov line, and there's also the circle criterion, which you can read in the book of Khalil, for instance. Okay, so there was this clash between the input-output approach, the operator theory, versus the state space approach of the differential equations. Okay, so what Popov did actually, he gave an input-output criterion to a truly nonlinear problem, and this is quite fascinating. So nonlinear has nothing to do with input-output operator theory because we can't work like that. We've seen this throughout this lecture. It's all about differential equations and differential systems and geometry and differential geometry and all these things. However, this guy, of course, for a special class of systems or for a class of systems, was able to provide a frequency domain criterion. Okay? And of course, the solution of the problem in the state space terms is based on numerical linear algebra. Yeah, that's why we do essentially state space dynamical systems, because we can do numerical linear algebra. And first, we'd like to formulate the problem, of course. What's the question we need to answer? We consider the following system. This is a class of systems. It's called Lure A systems. Yeah, with a static nonlinearity. So essentially, your nonlinear system can be written in this fashion. You split it into a linear part on the direct, on the feed-through part, okay, and then you add in a negative closed-loop reaction, you do a feedback connection with a static nonlinearity. So this is the class of systems studied in this problem. Okay, linear part and static nonlinearity. Okay, this is a feedback connection, mind you. Okay, so what happens here? You have the linear part, which is described by a linear dynamical system state space form. X dot is AX plus BU1. U1 is this guy. And the output, Y1, is C transpose X. We talk about single input, single output here, okay? It's single input, single output. We don't talk about MIMO in this case. And we consider the feedback. We consider the feedback Y2 a nonlinear function of the input U2. Okay? And then substituting U1 in the first equation of L, okay, U1, you get because here you can see U1 is minus U2 is minus Y2, yeah, so U1 is minus Y2, okay, and here we have that Y2 is the phi of U2, and U2 is Y1, so is actually CX, C transpose X, sorry. C transpose X. So essentially, this is phi of C transpose X. You substitute this in the equation, and you get that the closed loop system, the closed loop nonlinear system, written in this fashion, separating the static nonlinearity, is of this form. This is a closed loop system. Okay. I remind you that for linear systems, you had this. Okay. And here, essentially, you had this state feedback. Okay, and here you just put a block F. And you had that X dot in closed loop is A plus BF X. This is the linear case, the particular case of the linear systems. And the problem here was to find F such that the eigenvalues of the matrix A plus BF are in the open left half plane for stability, because you're interested in stabilizing. You're interested in stabilization. Okay, stabilize. You wanted to stabilize this system. Yeah, this is your nonlinear system, and you'd like to check the stability of this guy. The stability of this guy. Yeah, you can call this NL. Okay, and the problem is NL. Okay, having an asymptotically stable origin. This is the question we need to answer, essentially. So you do this interconnection, you wonder, you ask yourself, is this stable or not? The second question is, for which type of nonlinearities is this analysis good or fit? For which type of nonlinearities is this analysis fit? And it says here, given the system 2, this is system 2, with phi a function in R, under the condition that phi in 0 is 0, in a specified class, you'd like to find conditions on the coefficients of the linear system ABC transposed, such that the origin is of course, global you'd like, and it's actually going to be global indeed, asymptotically stable equilibrium point for any function phi in the specified class. In this case, the system, the feedback configuration is called absolutely stable. So this is the problem of absolute stability. Now, which type of nonlinearities is fit for this? The discussion is focused on the so-called sector type nonlinearities. If you remember, in the first chapter, in the introduction, we discussed about types of nonlinearities, and the sector type nonlinearities was one type, and the sector type nonlinearity is of this form. So phi is a function satisfying condition 3. And this is a sector sector type nonlinearity. Okay. Something like this. Something like this. Okay. Okay. Note that the system 2, the one with the feedback interconnection, is not precisely known. Is not known. The model is uncertain, so this is some sort of robust stability problem, actually. However, the coefficients ABC are known, and we have some information on the function phi. So this is the data we need to use to develop the absolute stability theory. Okay, some coefficients, and something about the function phi. Something about the function phi. Right. So, what's the approach in this case? Of course, you would like to find the appropriate Lyapunov function. Okay, this is what you'd like to have. A nice Lyapunov function. Okay. So, let's pick a standard Lyapunov function candidate. Let's pick something. Mind you, you have a linear part and a static nonlinearity. So essentially, you pick your energy function having first a quadratic term. This is peculiar to the linear part. Okay, and then for this function, you take this integral term multiplied or factorized by eta. You take this integral term for all x non-zero. This is a standard Lyapunov function candidate, and you can search in the book of Khalil for choices of this type many times. So many times you can start with this type of choice in many cases. P is a semi-positive definite symmetric matrix. Eta is a non-negative constant. And of course, you'd like to have V and W satisfy the conditions of Lyapunov's theorem. So first of all, you need to compute a so-called orbital derivative. So you need to do v dot x. V dot x. This is what you have to do. And I remind you that this is dv dx fx. Well, here they just did the computation. They just did the computation because we have to express something about this integral. So we take the time derivative of Vx. Hence, Wx is x dot transpose Px plus x transpose Px dot. This is how you apply it. This is Leibniz rule, okay? Leibniz, we discussed about this rule of derivation. Of differentiation, actually, not derivation. The derivation is in Romanian. Differentiation. Because you compute the time differential of this function. Okay. So this is x dot transpose px plus x transpose px dot plus eta, and how do you take the time derivative? So you take the primitive phi c transpose x, not the primitive, sorry, the function under the integral, okay, times what? C transpose x dot, okay. So this is derivation of f of g of x. This is the rule applied here. This is the rule that's applied here. Okay. Yeah. Okay. So this is how you take the time derivative of this eta term. Okay. And now you just substitute x dot. X dot you substitute using 2. Yeah. So this is using equation 2. You substitute it. Okay. And you end up, you do the computations and you make the notation v, but v depends on x. Note that v is v of x. Please remember that. However, we are trying to do or to mimic a separation of the variables. So you get this term. This is the quadratic. This is from the quadratic part. This is the Lyapunov equation term, or Lyapunov inequality term. And then you get these very nasty terms so far in this part. In this part, because you just do the multiplications here. Okay, so you have these leftover terms. You can still separate them if you separate them in something like Vx or xv, something like that. You can still achieve some nice writing. So Wx is this guy, and actually you can easily do that. You have this quadratic form or functional. This is not a quadratic function because v, I remind you, v is v of x. V is v of x. However, this matrix is constant. This constant, and we call this q, this function q, depending on x and v. It's a quadratic functional. And of course, the question is, how can you choose p and eta such that this is negative definite? How can you do that? And apparently, this is a very difficult task. You cannot do it like this. So we need further study of this functional, and we need further transformation of this functional up to a point where we can achieve an algorithm. Another question is, what happens if this term is negative definite? Then the inequality doesn't even have a solution. Okay. Furthermore, x and v, as you can see here, x and v are not completely independent variables. So you cannot just separate them and that's it. Can't do that. Okay, you can't do that. However, we have one additional piece of information we haven't used so far. Okay, that's the sector nonlinearity property, that phi is satisfied. So let's use that. Let's use that. And how are we going to use that? That's the question. Well, from condition 3, so from this condition, this is actually 3, okay, we described earlier. If you take this term, take it to this side and change the sign, right? Yes or no? You can achieve this condition. So is it true? Beta. Let's have a little bit of a look at the function phi. Piecewise continuous. Okay. Right. So this is phi beta sigma minus phi square is positive. So for some reason 3 is equivalent to this guy. Okay. B contains 0. Okay. So it from sector type condition 3, that inequality follows. That inequality follows. Okay. Right. You can check out how this is coming from 3. I don't see it straight away right now. I can't see it. However, with this, if this condition is true, so this is necessary from 3, and with the notations we make with V and everything, apparently you can write this. Apparently you can write this. So V is what? V is phi C transpose X. Sigma is C transpose X. And this is also V. So this is kind of clear. Okay. Right? And this is positive. This is positive. And if you relax this inequality, you can get the so-called S procedure. Okay. So as you can see, the selection of the Lyapunov function does not guarantee that things are very easy. Okay, things are not at all easy, if you can see. So it's difficult. I told you, Lyapunov theory can be really complicated. It's not so easy to assess the stability, to assess the condition of the Lyapunov theory. So the S procedure. So what you do, you introduce a constant and you add an additional term to Q. So instead of looking at Q, you look at Q plus mu times this positive term. So it's a correction you do to Q. Hence, if the function S is negative definite, it follows from this that Q is negative definite. Yeah, because Q, right? Q is S minus mu V times beta C transpose X minus V. And this is positive. So this is more negative. So if F is negative, it's necessary that Q is also negative. Okay, because you add a positive quantity to Q. Okay, and it says here, let's write explicitly what S x V, S of X and V negative means for mu equal to 1. And you explicitly write this this function. So you substitute you substitute Q, and you add this term, and then you just manipulate it a little bit, and you get here -1, if you can see here. So some terms are changing. Okay. And then the above inequality is satisfied if there exists a symmetric semi-positive definite P matrix, and a constant eta which is semi-positive definite also, or non-negative, such that the matrix D of P and eta, this is D of P and eta, which is this matrix, is negative definite. So this inequality is satisfied if this is called the linear matrix inequality, an LMI. And LMIs are very useful tools. LMIs are used a lot in optimal control with all sorts of relaxations. They have some numerical properties, although sometimes the problem might be a little bit ill-posed. There are people who are not so fond of LMIs. There are people who exploit too much the LMIs. It depends. However, this is an LMI. Okay, this is an LMI. Okay. Right. And there is a toolbox actually in MATLAB also, an LMI toolbox. Okay. However, the nice thing is we do not need to solve the LMI. This is the nice thing about this procedure. We need not solve the LMI. Okay. We are going to get another very nice condition out of this LMI. So the Lyapunov function method leads frequently to this kind of inequalities. Efficient numerical solution exists for about 10 years. Well, this is long before, so now you can say 20 years. Okay, or 25 years. So instead of solving an LMI, this is very interesting. One can alternatively solve a nonlinear system of matrix equations. A nonlinear system of matrix equations. And what do? You just write S of X and V is negative and you pick the constant mu to be 1 over beta. And in particular, you take V to be minus U0 and X to be this quantity, J omega I minus A, all inverse times B U0. With U0, any number, any complex number, and omega frequency, any real number. And you denote the real part of the system, GS being C transpose SI minus A inverse B. Okay? And Okay, we are going to skip this part. After some tedious manipulation of the things, you end up, so actually this is equivalent to solving this inequality, Okay. And we know how to do this. This is similar to the Nyquist criterion from linear systems. And now we are ready to formulate the criterion of Popov of or for absolute stability. Okay. So we consider the Lure system with a static nonlinearity on the feedback, as in figure 1, and assume the following assumptions. The transfer function is irreducible and has no poles on the imaginary axis. So we have to be careful about this condition. There exists a K such that A plus minus BKC transpose is a stable matrix. Okay. And 3, there exists eta such that this is positive for all the frequencies omega. Then the system is absolutely stable for all sector type nonlinearity satisfying condition 3. That's the sector type nonlinearity. So this is a frequency domain on a linear a frequency domain criterion for a linear system. Of course, this has a graphical interpretation if you look in the phase plane. Okay, real, imaginary. The frequency domain condition can be expressed similarly to the Nyquist stability criterion using the frequency response of the transfer function GS, which is something we know from the second year. So now you write 5 in terms of U equal to the real part of G of J omega and V the imaginary part of J omega. And then you get this inequality. The above inequality defines a half plane in the complex plane of the so-called Popov plot. This is the Popov plot. And the functions of the Popov plot are these guys. And then you can obtain this guy. And this is the condition you have to face. Now, look, this is a straight line. And you have beta here. Okay? So you have to have something like this. Okay? Consequence, under the assumption of the theorem 1, the system 2 is absolutely stable if the Popov plot is entirely placed to the right half side of the so-called Popov line. The Popov line is this guy. It's a line, you see. Popov line. This is a line. In other words, the Popov plot must lie in the same half plane as 0, essentially. As 0. Okay? This is the slope of the Popov plot. Eta is the slope of the Popov plot. The line is intersecting the U tilde axis at point -1 over beta, and the slope is 1 over eta. The slope is 1 over eta. Okay. So this is how it looks. Okay. This is the Popov line. Okay. This is the Popov plot. Okay. And this is the modified Nyquist plot. This is for this function. This has no poles on the imaginary axis. Okay. This is how it looks, and indeed it's absolutely stable. And you see the Popov line, which is this one. Okay, so this is 0. This is 0 at point so V equals 0, point U equal -1 over beta. Okay, and the slope is indeed 1 over eta. Okay, 1 over eta. And we have some examples here. GS is 1 over S plus 1. U omega tilde is this guy. V tilde omega is this guy. You can choose eta equal to 1. And the question usually we ask is how large can beta be? And what's the largest sector for which the absolute stability can still be guaranteed? Okay, these are the usual questions we are trying to answer. Okay, right. Let me check now for some examples in MATLAB or in Maple. And that's it. This is a short chapter. And next week, we are going to start talking about the so-called feedback linearization. Okay, feedback linearization. Actually, we are going to tackle the subject a little bit today. And the core part of the subject we are going to talk about next week, and then continue a little bit after the holidays, and then we stop, because you've got a lot of theory, you've got examples, you've got papers, you've got enough material to do. This is, I remind you, please do not forget that this is, or mind you, this is a research master. So you have to do and present research. Okay, you've got enough material. You can do your own research in this case. So let me try and show you some examples. Let me show you some examples. I have something in Maple. Let me share another screen. Okay, so stop presenting. I'm not presenting from the tablet any longer. I'm going to switch to the I'm going to switch to the other screen. Oh, so it's only the two of you left. The rest are gone. No problem. Don't mind. Please do confirm that you see my screen. Yes, I think you can see my screen. Can you see it?
Yes, we can hear.
Wonderful. So I'm selecting the linear system, this guy. Okay. And I'm taking, let's see, first of all, so I have to select here. I'm taking this transfer function. Okay. And I'm going to run this sheet line by line. Line by line, okay. So this is the function. Look, you have a pole in 0. You have a pole in 0. Let's see what happens. Assume omega is positive. I compute hg omega. So h evaluated in S equals j omega. This is it. Then I take u, the real part of hj omega, which is this one. And here I'm taking, so this is u tilde and this is v tilde, but I'm not using the notation with tilde because it's complicated. And this is omega times the imaginary part of hj omega. Eta equals 1. This is the Popov line. Okay, this is the Popov line, and this is 1 over beta, as you can see, because U and V are pretty much the same if eta equals 1. Okay, taking beta to be 100. Okay. I'm plotting the Popov line, and this is the plot. You see, this is the plot of U and the Popov line. So here I'm plotting U, V versus U and D and dP. And this is the Nyquist plot of the system H, which looks a bit different. You see, of course, because you have a pole in zero, you have this vertical asymptotes, if you remember. Okay. Right. So you have a pole in zero, so the results are not so good. Let's see if we take a different eta. What happens? 1, 2. Let's run this again. You see? So it's not stable. It's not absolutely stable because the criterion is not fulfilled. The red plot should be to the right side of the Popov line, the blue line. The blue line, okay? Blue line. Okay? Yeah. Because the Popov line is this guy. Is this guy. Okay? So V is 1 over eta U. Okay? Yep. Okay. Right, another case. Let's go to a better case. So this is not stable. This has a pole in zero. This is not right. Let's go to the simple case. Let's go to this guy. Hj omega. It's the guy from the last slide of the lecture. This guy. So this is H. This is U. This is omega V. We pick eta half. The Popov line. You see, the Popov line is this guy. Yeah. So how far can we take beta? You see, so omega is anything. So beta, the largest beta is this guy, of course, in absolute value. We do the same. So this is the Popov line. And look, this is the Popov line, the blue line. And indeed, this is absolutely stable. Why? Because the red line is on the right-hand half plane of the Popov line. Now let's take beta. Let's see what happens if beta is larger. Run again. You see? Okay. Let's take beta smaller. So things are all right, you see? So you can take beta even much larger. Let's take eta equal to 1 and run again the sheet and see the results. You see? So the line, because the slope, the line is, it's still, so no matter, so beta is essentially what? Beta is infinity. Beta is infinity. You can take beta as much as you like. as much as you like. This is always asymptotically stable with the origin is asymptotically stable with a sector type nonlinearity. Okay, let's take another example. We have here 3 poles, 2 of them complex conjugated, and 1 of them real. Let's run this and see, and then check out the results. Okay, so this is the transfer function. This has no poles on the imaginary axis. This is actually an asymptotically stable transfer function. We compute everything. This is the Popov line. This is the simplified version of the Popov line. Okay, and this is how much can beta be. And this is actually, it cannot be that much, because look at the plot. This is not stable, you see. This is the plot of the U tilde omega and V tilde omega. And this is not right. Everything should be under the blue line. So this is not good. Let's see, let's change eta and see what happens. So we change the slope. Do you think it will change anything? No, it's not changing anything, because it's not about the slope here. It's not about the slope here. So the slope can be left 1, can be unitary. The problem is about the beta. Let's start with a small beta. Let's start, you see, small beta, small beta. Now the origin is asymptotically stable, so the system is absolutely stable this time. Okay, now let's increase beta by 1 order of magnitude. Let's run the simulations. No, it's too much. So beta cannot be that much. Cannot be that much. Let's put it like this. So beta is limited, and you can actually compute beta 20. You see, you can actually compute the largest beta possible. The largest beta possible. Let's take it like this. See what happens. Oh, so we're still all right. Right? Oh no, sorry. Like this. We need to have beta larger. No, this is too much. This is too much. I don't remember, how did I do it last time? This is not good. 0.5, 0.8, like this. Sorry. Oh, so we are still all right. We're still all right. I want to increase beta, you know. Oh, it's too much. It's not good. It's not good. So increase. So 50 is not good. I'm just trying to guess. Oh, so this is in the limit, you see? So it's about 34. So this is the max beta for which this is still absolutely stable. This is still absolutely stable. Yeah, this is the largest sector actually, because beta from inequality 3 indicates the dimension of the sector type. Okay. All right. Okay, another example. Let's change the function h. Let's take this guy. This is a second order system. Okay, a stable system. You see here, look. Again, you cannot go with beta as large as you like. You can't do that. Let's see if we can do 0, 0, so we can have beta 100. Okay, yeah, it's still there. It's still there, if you can see, because look at the plot. So essentially, you can also play with the slope here. So you can take eta to be, so you actually decrease by a factor of 2 the slope, you see, and you can increase, look what happens to the Popov line. You can increase beta. Let's see if we can do it by an order of magnitude. This would be really, really interesting. Well, it actually doesn't matter. It doesn't matter. So actually beta in this case is infinity, you see, at this slope. So you can also play with the slope. You can also, if you take the slope, okay. Now this is not good, you see. So here you play with the slope. The slope eta is also important here. So it depends on the choice of eta as well. Okay. What else? Let's see what happens if you have a 0 in 0, for instance. Oh no, this is on the imaginary axis. Let's see if you have a 0, and so you have a non-minimum phase 0, and you have two poles, two stable poles. Let's see what happens this time. Well, this is very complicated, you see, so it's not good. It is not good. So let's change what? Let's change the slope. Let's change the slope. We need a good slope as well. And we also need a good sector. This is not so good. This is not so good. Maybe for larger beta. Okay. So the geometry tells us exactly what to do. So apparently we cannot stabilize this guy. Although it's stable, it has a 0. It has a non-minimum phase 0. Let's give it a minimum phase 0, so a stable 0, and see what happens. You see, with a stable 0, things are very nice. There is no problem any longer. But the non-minimum phase 0 complicates the things, so you cannot use this criterion. And actually, this is very much along the arguments that in general the presence of an unstable 0 in a system makes the control complete much harder, increases the presence of an unstable 0 may, I would say, increase exponentially the difficulty of the control problem. Okay. What I don't know now is if I have some examples in MATLAB for the same problem. So let me check. If not, I invite you to build your own MATLAB sources for this thing. MATLAB. Okay, nonlinear systems. No, it's not this guy, apparently. So let's go. Let's go to what? Let's go to the teaching once again. Nonlinear systems. No, I don't. Apparently, I haven't got. I haven't got. Apparently, but maybe I should. Hold on. Software. No. Do not. I'm afraid I haven't got a MATLAB code for this absolute stability. So essentially, you can't do Nyquist. We can check, actually. We can check it together on the spot. And check what? Check how you do Popov criterion in MATLAB. I think this is interesting, and we can search together. We can research together. Okay. Right. So now, Popov criterion MATLAB. You see? MathWorks. Okay. New page. Can you still see my screen?
Yes.
Oh, yes. Apparently there is a function. There exists a function, Popov robust stability test. Possibly nonlinear time varying uncertainty. So look, this works for time varying as well. It's nominal LTA system, okay, Lure system, okay, fine. So TPSN, Popov of cis and delta. Stability is going to be okay. How do you put delta? So apparently there is let's see some examples. No, it's not what I expected. Once again, Popov criterion. Let's tell them we're in the Netherlands. LMI. So it's in the mu analysis. You see? This is not very useful. Who is delta? How do you do delta? I can't tell. LMI applications. Okay. Stability, RMS gain, LQG performance. And where's Popov in all this? Not much. Not very useful. This is a ResearchGate, apparently. I very much like some code, if you ask me. So you see here, Popov criterion. It's described again. Oh, view full text, okay. All right, where's the code in that? Okay. And there are some, if you can see here, there are some commands. Can you see? Popov, num, den, and 0. Let's try this in MATLAB. Will you? So, num, just building up a transfer function. One. F. Let's see the transfer function, num, den. So this is the simple transfer function. And he says here Popov, num, den, and what else? Num, den, and 0. Ah, 1 is circle criterion, 0 is Popov criterion. No. System matrix help. Oh, it's different now. It's different, you see what this guy says. Interesting.
Maybe he wants
H?
a state space representation.
Not necessarily. It says sys. What's flag? Oh, flag. Let's do like this. No, it's different, you see. I don't get it, because here there is one type, uses. What the hell is uses? Uncertain continuous state space model, CUSS. Ah, okay. So you have to create a special type of system, you see. Uncertain. You have to build the uncertainty. You have to build the uncertainty. You see, you have to do it like this. I understand. I mean, I'm puzzled by what's going on in this reference, because in this reference you do it like this. But who's the function Popov? That's the question. No? That's my question. They use a function Popov, but it looks like it's something different. To be honest, I haven't got any MATLAB code for this, so this is kind of new to me. I have liked very much to see these plots. This plot, I'd like to show you these plots. Num, then, okay. Stable plant F, num, then 0. Where did he get these functions called Popov? Because this is totally different from what I see in MATLAB. Which year? What year is this guy? 97. Ah, so this is long before. No, this has changed completely. Okay, I understand. I understand. Well, anyway, I have Maple for all I care. I'll check this MATLAB thing if you can do. So please do research, and if you can build me a code for the Popov criterion in MATLAB, a simple code, not necessarily, or you can understand and decipher what the Popov function does in MATLAB. Please show me, okay? Please show me. Right. Okay. I'll unshare this thing. And now let me try to upload part of the final subject, like I said, of the second type of control method based on Lyapunov theory, and that's feedback linearization. Let's see what we can talk about, what we can show. Feedback linearization. Okay. Insert, and here I have many materials. I think they are uploaded on Moodle already. So we're going to start with a subject described by my former colleague Alexandru Țiclea, who left our department 2 or 3 years ago, and okay, and see how things go. So let me share this screen again. Okay. I suppose you can see my screen. Yes, you can, indeed. Feedback linearization, okay. Now, this is another truly, no, oh, this is in Romanian, I'm afraid. Oh. I also have some slides in English, okay. So I'm going to explain. For Florian. So essentially, we have this type of systems. So we consider this type of systems. These systems are not autonomous any longer, but they are forced because they have an input U. Okay, so they also benefit from having a command law, okay? a control law. Okay, so this is the class of systems. Note that the control law, note that the first equation is what's called affine in the input U. So this is not f, x, and u, but this is of this specific form. Okay, right. And here you have x in Rn, u and y. So this is also single input, single output. Okay, and we'd like to see. So this is u. This is x dot is fx plus gu, gx u. Sorry. fx plus gxu. This is the output y. Okay, and we'd like a feedback linearizer. We'd like a state feedback. Yeah. So this is alpha x. Okay. Alpha x plus, and here you have beta x. Okay. And this is also having an external v, and you have this closed loop configuration, and you'd like this closed loop system to satisfy some specific properties. So you would like to find this type of control law and a change of coordinates like this, such that the transfer from v, the input v, to the output y is described by a linear system. This is what you want to have. So you want to have this linear. This is the main problem of feedback linearization. Example, a forced pendulum. Yeah, this is a forced pendulum. Is this guy. Okay, U is the control law. We would like to cancel, okay? We'd like to cancel the nonlinear term. Can we do that? Yes. How can we do that? How can we cancel the nonlinear term? We take the nonlinear term to be, we take the input u to be 1 over c times a sine x1 plus v. Okay, this is what we do. And then finally, you get a controllable linear system. It's linear. You see, the nonlinearity is gone thanks to the choice of this control law. And further on, we can build a state feedback to stabilize the system. A state feedback, this is not stable if you look. Yeah, this is not stable. Not stable because the function is 0, 1, 0, minus b. This is the a. This is the linear system, yeah? So this is ax plus bv, and a is of this form, and this is not stable. Not necessarily stable, okay? So we'd like to stabilize this. We'd like to stabilize this, and then we build an additional state feedback, okay? And we to stabilize the system. And then the final control law, because you substitute v, you substitute this v in here, is this guy. So this is a simple example. Of course, things are not so simple as described here. We need a little more than this. Okay? And we have input to state linearization, and we have input-output linearization. Okay? So we have a convenient structure to cancel nonlinearities. Convenient structure to cancel the nonlinearities. Okay? This type. This is what you want to have. So essentially you have x dot is ax plus bu, and u is of the type gamma x, okay? No, so this is not u, this is v plus bv. Okay, and v is of the form gamma x times u minus alpha x. Yeah. Okay, because alpha x, u is alpha x, plus gamma x or beta x v. We need to have the pair AB controllable, of course, and the mappings alpha and gamma are defined somewhere on a domain where the origin is contained. And also gamma is non-zero for all x in the interested domain. Okay. Linearization is possible selecting U of this type where beta is 1 over gamma. Okay, so linearization is possible. And the linear system, once you apply this control law, the resulting linear system is this. And if you want to stabilize further, you pick this state feedback such that this is a Hurwitz matrix. This is a Hurwitz matrix. Okay. So this is if you want to do input to state linearization. Now, the convenient structure through a change of coordinate, because you cannot always get this structure. This is what you'd like to have, but you can't get that always. So you need a convenient structure. Through a change of coordinates. Okay. So for this system, if you have this simple system, look at this system, and you change the coordinates of this type. These are the new coordinates, z1, z2. Then you get in the new coordinates, the system is of this form. Because x2, you see sine x2 you have here, and x2 dot is this guy. Okay. So z2 dot essentially, so that means here that z1 dot is x1 dot, and here z2 dot is a cosine x2 times x2 dot times x2 dot, and x2 dot is of this form. So you get this convenient structure. And what is the control law if you want to have this thing to be linear? You take this control law. So this is a cosine x2 times minus x1 squared plus a cos x2 times u. So essentially u is this guy. And then you get it linear. But can you also linearize this from an input-output perspective? Because in general, it's hard to measure the state. You have information from the output. Okay? And then you have hidden dynamics and other things. Okay? So this is just an introduction to feedback linearization, which we are going to get deeper starting next week. I think we should stop here, and I'm going to ask you for questions. Have you got any questions, please? Have you got any questions, please? I'm waiting. Have you got any questions, please? Have you got anything to tell me?
I don't have any questions. I found on file exchange MATLAB an implementation of Popov.
Okay, nice.
And,
please upload it on the file sections.
yeah. Firstly, I will check it.
Yes, please do.
It's correct.
And if you can make a nice M file, please show it next time.
Yeah.
Yes, please do that. I'm really curious about it. Okay. All right.